Well, good morning, everybody. So this is the second of my lectures about n-body simulations. So in the first one, we went through these steps. So hopefully by now you have an idea of what the numerical simulations are, the basic assumptions that we make, how we compute initial conditions, and how we can evolve our equations of motion over time. So, I think it's maybe it's just a blackboard. So I was mentioning yesterday that as with any other numerical method, when we integrate of equations of motions, we are not doing it perfectly, but there are errors associated to this numerical integration. So there are particular parameters and values that you need to choose to have a proper converged solution. Would depend on the particular code and problem that you have in hand. So it's always a good idea to perform different numerical experiments on your problem, to vary, for instance, the softening length, the accuracy of the integration, of the force, and so on. So to make sure that you reach the accuracy that you require. So this is very important in the field of large-scale structure because future observations of the distribution of galaxies and cosmology will be much more, will set a very high bar in terms of accuracy. So we need to match and surpass that accuracy with our simulations. So we need to understand our sources of errors and how to minimize them. Right, so from our numerical simulation, the little n-body code that we wrote, we can now predict what is the nonlinear power spectrum of density fluctuations. So this is the power spectrum as a function of scale, like 1/scale, right, the wavelength. And the linear theory solution is the solid lines, and these different colors is time. So this early time, this late time. And now if we solve our equations numerically, not using perturbation theory, we get the symbols. See that high redshift, the fields are pretty linear, so our linear theory is a good description. But as time goes by, gravity acts and the field becomes nonlinear. Even though on large scales, we still have good agreement between our numerical results and linear theory. On small scales, their two results differ by quite a lot, by maybe even an order of magnitude. Right? So this is the nonlinear power spectrum that would be measured, for instance, through lensing. So, so now you see that we can ask how well can we make predictions for this nonlinear power spectrum. So this shows the prediction for this quantity relative to a reference run as computed by different codes, like there's Ramses, PKD Grab, Gadget, and Abacus. So you see that on large scales, where linear theory dominates, or is a good description, things agree pretty well at the sub% level. The same is true for the quasi-linear regime, but in the highly nonlinear regimes, you start getting the differences between different codes. Some of them predict a higher power, other not so much, right? So the differences are about 1% at up to k of 1. So that means up to roughly a few megaparsecs. But when you go to smaller scales, like intra-halo scales, the differences can be up to 5% or so, right? So to give an idea, Euclid, this future European space mission, will measure this nonlinear power spectrum to about 1% precision. So this is telling you that we need to understand the differences between these codes and reduce our errors. Otherwise, future constraint might be dominated by this type of theoretical errors, not by the data itself, right? Yes? Right, so then, so this is two different ways of doing the softening length on a small scale. So the one I show you is essentially adding an extra term to 1/r, right? And that is usually called a Plummer softening. But you can also do it add other type of smoothing functions, and this is another choice, the spline. So it just tells you how compact or extended the softened forces are. Right? So. Right, so there are actually quite different. Abacus on a small scale, that's, I believe, mostly direct summations. Ramses is a AMR, so it's like a PM like the particle mesh code, but that adaptively refines the cells in the regions where you need it, even for the dark matter, yes. So the particles themselves are still, or the dark matter is still particles, but the force field is given by a adaptively refined mesh. So you cannot use directly FFT solvers for that. You need other methods, but the basic idea is the same. You just solve the Poisson equation on a mesh, but that's not regular, but it's different. PKD graph is a pure tree code. So that's there are three calculations, actually a fast multiple all the way, even on very large scales. And gadget is a 3 PM, so it means you use a multiple expansion on small scales and the PM on large scales. So maybe related to maybe these differences are related to that, right? So the way you compute forces, also the way that they apply the softening length is different, and the way in which they especially different parameters, they choose different ways of doing the time integration also. So it's not obvious actually how to make a proper comparison. So rather than saying that this is the actual differences between the code, I tend to think about it as this is the maximum, at least a lower limit to the accuracy that you can achieve. Right? Probably by tuning the parameters further, you can improve the agreement, but at least they can get to 1%. So those numerical choices should be at least, or they should be smaller than 1% on these scales and 5% on these other scales. No, so gadget is actually this one. So it's the one that deviates mostly, is gadget. And Ramses, I believe, is yes, this one. And the other, PK graph is the cyan, and the other. Well, so these are ratios with respect to this abacus blue line. Actually, I wanted to go a bit further on this. So this is actually how much the power spectrum changes when we vary different numerical parameters in gadget. Right? So this is the same as before. The difference with respect to a fiducial power spectrum as a function of scale. On large scale, doesn't really matter how you solve. You tend to have the correct answer anyway. But on a small scale, you have differences actually of 5% or so. When you change, for instance, the maximum step that you are allowed to have, or the maximum error that you want to have in your time integration, or how you are actually doing the transition between a PM and a 3/4 force calculation, and what is the error that you want to associate to the force calculation. You see that this can change quite a lot your answer. So it's also very important that you keep in mind all these if you're interested in running not only numerical simulations, but any numerical experiment, right? But you could say, well, these are just numerical parameters. Why don't we just improve them to the very, very high accuracy? And the problem is that the execution time of this numerical simulation scales and depends a lot on the values of these parameters. So this is just telling you how long a numerical simulation would take for different combinations of parameters that I was showing you earlier. So based on what you actually choose, you can change the execution times by factors of 4. Right? So instead of something taking you a few days, it might end up taking weeks. Right? So actually, you have to find a set of optimal parameters that solve your problem with the required accuracy and provides the least amount of execution time. Right? So you are faster, the shortest time to solution. But these are numerical parameters. There are other parameters that control the accuracy that have to do mostly with the physical setup of your problem. So this is the same type of plots, the difference in the power spectrum as a function of scale. But now if you change the volume of your calculation, in some case you can simulate only like a 200 megaparsec box. In other cases, you're simulating something of 1 gigaparsec. So you see that if you start simulating regions of the universe that are not very big, you start systematically underestimating the amount of nonlinear evolution that there is in the universe. This is essentially because you're missing the coupling between long modes and short modes. So in this right-hand side panel shows you that what would happen if you vary the number of particles in your simulation. Essentially, now if you start discretizing your phase space now with more and more particles, you would end up with a different result, actually. And then if, for instance, in this case, if it shows the difference between using 200 cubed particles versus using 2,000 cubed particles. You can see that on a small scales, when you use only a small number of particles, you tend to underestimate the amount of nonlinearities by up to 10%. So the reason behind this is that when you don't have enough mass resolution, you are not able to resolve the very small structures that that the universe should have. Right? So then you are missing this amount of nonlinearity in your solutions. So this is something that the community is worrying a lot about it and trying to understand in more detail how all these effects are in play and how we can make robust predictions. So in summary, I think if you want to have a 1% accuracy, you can make predictions up to roughly k of 1. You need to start your simulations at very high redshift, and you need to use more than 500 megaparsecs on a side, and your particle mass should be below 10 to the 9 solar masses. So these requirements translate into simulations that are roughly 4 gigaparsecs and more than 4 trillion particles if we want to achieve the volumes and the resolution that future surveys like LSST, DESI, or Euclid will require. Okay, so this is essentially the stage. Now we have the numerical methods, we understand the noise, and we have a target, right? The type of simulations that we need to be carrying out. So I wanted now to review briefly a bit of the history of numerical simulations and how we have arrived to where we are now. So I believe the first ever numerical simulation was done by this Swedish astronomer Erik Holmberg in Lund Observatory. And the setup that they did was quite clever. So it was on a table, and then they put light bulbs on this table, and then also essentially photoreceptors that you could measure the light that was that each light bulb was receiving from the others. Right? As the luminosity decreases as 1 over distance squared, the same as gravity. Now from these galvanometers, you could measure how much light was receiving, and you can translate that into a gravitational force. So they were actually writing down for each of the light bulbs what was the intensity of the light, and they were actually then moving them by hand. And actually, what this probably you can imagine is also one of the first algorithms for embodied simulations, right? It's just that the algorithm was not purely computational, but was actually mechanical and human, right? The human has to do something. But interestingly, when you start with these two sets of light bulbs, and then you let them interact, you start seeing the appearance of all these tidal arms, right? So something that is quite hard to predict only by looking at the structure of the equations, right? So it's another example how a numerical experimentation on a set of mathematical equations can lead to interesting insights about the underlying physics. So it happened until the 70s when you start actually having numerical simulations done in computers. And some of the first one in cosmology were done by Jim Peebles and on a Stryker. And these were pretty much at the same time that the first computers were available, so it's quite impressive. And then they started solving for the evolution of this rotating group of 300 particles. And then they realized that if you just let them evolve, they would very quickly end up in a collapse structure in the center. It actually was a bit puzzling for them because they were trying to mimic how the galaxies were. So they were saying, oh, why don't galaxies just go down and settle in a small clump in the center? But anyway, so these were very essentially isolated initial conditions, essentially one group of particles, and then just let them evolve. Some of the first, mostly like cosmological numerical simulations, was done by William Press and Paul Schechter. So they were setting initial conditions, Gaussian initial conditions, random Gaussians, and then letting them evolve. And then they were measuring how much mass was in objects of different sizes. And that led to the development of the very famous projected formalism that is even used today, and extensions to it to the 90s now. I think are probably one of the foundations of our of an analytic understanding of how structures assemble in the universe. So in parallel, there was in the Soviet Union was also work done by Doroskevich and Sandarin and Seldovich, I believe too, where they were also doing simulations of the collapse of different random waves. But up to that point, essentially people were just creating, they didn't know really what to simulate. So they were creating different setups or Gaussian random fields, sine waves, and so on. Because there was not really a good model for the initial conditions, right? So in the previous lecture, I was telling you that you know the equations, but cosmology is mostly an initial value problem, right? That you need to know how to start. And that was not clear until the 80s, where there was the development of the theory of inflation. Different candidates for dark matter started to be more concretely defined. So you have something more, a full model that you could test and simulate. And this was a work done by Davis, Stafford, Frank, and White, where they did exactly that. They took small simulations of different type of dark matter. So in some cases, they were simulating essentially neutrinos, very hot particles, and the other, they were simulating cold dark matter. And then they were letting them evolve, and then they were developing a way of placing galaxies in them. And then you start seeing them that they qualitatively predict very different results. So for these were the hot dark matter, and then you see that all the galaxies, which are these dark dots, would cluster a lot in essentially very dense clumps. This is because in hot dark matter, there is actually very little small-scale structure. Whereas in cold dark matter, you had more places where galaxies could form, and then their distribution was more homogeneous. And by then, there was actually the first galaxy surveys being conducted, and this was actually the observations. This was the CFA survey. And then you start seeing that, well, actually it looks much more like cold dark matter rather than hot dark matter. So yeah, I think there was just a lot of caveats to this argument, but it's a good example of how we start using our numerical simulations to also get an understanding and information about the real universe, right? In this case, pointing towards the existence of cold dark matter rather than hot dark matter. So in the 90s, the simulations kept growing, and the surveys also started to get bigger. So this is essentially it's a simulation now, a much larger volume, much better statistics. And now this paper of Stafford, Sutherland, and Maddox, they were playing with the amount of dark energy. What would happen if the universe is completely matter dominated, or what would happen if it has some non-negligible amount of dark energy? And they were finding that the clustering would be very, very different. And in that time, there was the APM survey, so you can see here, and actually the measurements were like this. And then you sense, again, with some caveats, but you start seeing actually that the universe with a cosmological constant fits much better the data. And actually in their paper, they argue that you still can have the successes of CDM if you have a spatially flat cosmological constant, spatially flat universe with a 80% of cosmological constant. So since then, the numerical simulations have kept growing in complexity, in the detail, in the realism. And this is showing you the number of particles in the simulations as a function of the year. So this was the first simulation I showed you, Peebles, and there were some by Simon White, Arset, the Davis simulations were here. And since then, we have grown exponentially. Right? And now some of the largest simulations, well, here you can have the Millennium simulations with 10 billion particles. And so we have essentially keep growing even faster than the available computational resources, which is this Moore's law is here. And I wanted to show you a movie of it's a movie of a simulation that I conducted in 2010. Was one of the largest simulations at that time. So you can see now we are flying through these simulations at the speed of about 100 megaparsecs per second. And now you can see all the filamentary structures here in blue, and the places where galaxies form are these yellowish. And now we are getting close to some of the actually the largest halo in the simulation of a mass close to 10 to the 16. So the whole calculation followed 300 billion particles on a 70 cubic gigaparsec volume. So you can see that the whole cosmic web can be resolved very accurately with these numerical simulations. Right, but despite all these improvements and now these humongous simulations, still the requirements that we were discussing earlier are not met, right? So still we need even larger simulations and more accurate, and that poses a very strong, very hard challenge computationally. So the simulation I just showed you, the Millennium XXL, so essentially the act for its completion, it needed like a few quadrillion force calculations. So you need to have a lot of CPU power to resolve this. You have huge imbalances because you need to resolve the center of clusters where dynamical timescales are very short. So you need very good accuracy in integrating, and at the same time you have regions of low density, so where the timescales are much longer. The amount of memory that you need for the simulation is also gigantic. That's typically more than a few hundred terabytes of RAM are necessary just to hold the positions and velocities and IDs of particles. If you want post-processing, you need even more of computational power. And then there is a lot of data products being produced, and typically can be of the order of petabytes if we want to even store or read the initial conditions or store the distribution of particles and so on. So these are very tough computational problems. And then, so that actually leads to the need of high-performance supercomputer. So I wanted to spend a few minutes discussing what is high-performance supercomputing and why is needed. So in numerical simulations, but in also many other branches of physics, we need high-performance computing because essentially 3 reasons. One is big data, right? So now, as I mentioned before, the amount of data that you're producing is huge. So you would like to analyze it in an efficient way, be able to quickly search for different aspects. I want to, for instance, look for a particular dark matter halo, or I want to be able to process and compute a number of voids in the simulation. So you need to have a ways of efficiently process these huge data sets. It's also big science in the sense that we need, so we want to be able to use the best hardware available to us. So we want to improve always in the type of simulation that we want to do, not only sustaining the volume, but we want to improve the realism in which, how we follow the merger history of halos or treatment for placing galaxies, making more accurate assumptions and so on. So this is always pushing us to do the best simulation we can, the best numerical solution that we can, using as efficiently as possible what we have available. And then also with this new high-performance computing, we have access to the new science, and it's not only solving the same problems with more and more particles or with better resolution, but we can also do problems that we couldn't have done before. So for instance, now we can explore variations to the law of gravity or systematically change different assumptions, something that we could not have done in the past. So to actually be able to do all those things, there is one key concept, which is parallel computing. Right? So if we want to, essentially parallel computing is essentially the way that we can solve our problems using not one CPU or computer at a time, but multiple computers concurrently. So if we are able to do this well, we can now solve the solved problems, but in a faster way. We can solve for bigger problems, analyze larger data sets, and we can at the end do more science. So this is actually a key concept in high performance computing. So if you like computers, or if you have been interested in this type of problems, you might have heard of the Moore's law, right? So the Moore's law was an observation done by an engineer in the 70s in the Bell's lab, which tells that he noticed that the number of transistors in an integrated circuit doubles every 2 years, right? So, and actually this trend has continued all the way up to today. So this is a plot showing you the number of transistors as a function of year. So in the 70s, where the first numerical simulations were done, where there were only about a few thousand transistors. Nowadays, some of the largest ones contain 20 billion transistors, right? So this trend keeps going, and well, there might be limits actually in the future, right? But so far, this has been remarkably consistent over 40 years. Right, so now we can see, well, this is a good news in some sense, right? So we've been following this Moore's law with our numerical simulations. We have keep growing. So you say, well, we just have to sit and wait for computers to get faster, right? But actually, the Moore's law has been, in terms of the number of transistors, have been kept constant. But that doesn't mean that the computers are getting faster. So this is showing you actually that actually quantitatively that is actually not the case. You might actually remember. Maybe you're too young, but actually, if you think of 5 years ago, the computers were 2 gigahertz or something like that, right? Today, they're still 2 gigahertz. Whereas, but if you go back to the 90s, they were about 300 megahertz. So this is what is showing you. Essentially, the computer power had been increasing up to roughly 2005 or so, but then they has actually stagnated. The supercomputers, the computers themselves are not getting faster, right? So this is the frequency, right? So it has pretty much stayed in like 2.5 gigahertz. So the reason for that is actually thermodynamics, right? So is that the amount of power that this transistors are generating is so huge that you cannot be dissipated efficiently enough. So you cannot really compute faster. So you might have heard of people that take computers, they put huge coolants, and when they actually manage to bring them down, they actually can speed things up, right? But in normal setups, you cannot do it. Actually, if you go to a supercomputer center, it's very impressive to see all the machines, the racks with the servers. But actually, probably even more impressive is the cooling system that they have. Right, so the amount of energy that they need to keep the computer cold and that for it not to melt is actually huge. And it's actually this is what is the limiting factor for speeding up computers. But you say, like, the number of transistors have kept increasing, right? So what is going on? So the way that the industry has solved this is not by making each computer faster, but by putting many computers inside the same chip, right? So essentially, it's increasing the number of cores that a CPU has. And now this is what is shown here, right? So before you have only 1 core per computer or per CPU, up to roughly the same place where you start stagnating in frequency, and the number of cores has increased. So a few months ago, the largest CPU was released and has almost 100 cores. Right, so now you can see that this is everywhere, right? You could look at your cell phone, right? That has even 4 or maybe even 8 cores, or your laptops have, and this is probably what's going to keep going, right? So the number of cores increases, but not the computers are not getting faster. But this is pushing us to change the way we were doing numerical simulations, right? Because now when you look at the large supercomputers, so this is showing you the amount of computing power there is as a function of time. So this is the largest supercomputer that there is. It's in China. It's like 10 millions of these CPUs, right, that are put all together. Right? So it's 1.3 petabytes of RAM. So it keeps increasing, but now we know that this, and now if we want to keep pushing ourselves and in numerical simulations to be able to be able to do the state of the art the best we can do with these resources, we have to take all these changes into account. So this brings the idea of parallel computing, right? That we don't, now it's not like you do a sequential algorithm and just solve it, but actually we need to think that we want to split our problem into many, many different chunks and solve them concurrently, right? Because our different cores will be solving different parts of our numerical simulation, right? So ideally, you kind of split your problem, and each of the chunks is done by a different core, and it doesn't really matter the order in which you do it, and no, life is good, right? So this would be an example of how it would be. You split your problem into 3 chunks. You give it one chunk to core 0, another to core 1, and core 2. Each of them progress independently, and they deliver the results, right? So when you have these problems, actually we call them, actually this type of problem could use even the largest supercomputer in the world very, very efficiently, right? You just split your problem into 10 million chunks, and you're done. But the thing is that very rarely this is the case. Actually, these type of problems are called embarrassingly parallel, because they're really not parallel. It's just you're doing the same calculation all over and over again. In reality, you actually, in particular numerical simulations, you have a different type of problem. Right, so so now you want to imagine that it's your volume, and now you want to split it into, in this case, 4 different chunks, right? So different parts of the code actually they find a different way of optimally splitting the problem. So, for instance, for the tree calculation, they usually follow actually a fractal curve. In this case, a Peano-Hilbert curve. So it's a curve that kind of walks through all the domain, and now you split this curve into chunks, and you give one chunk to each CPU, right? So for instance, here I'm going to start walking it. I stop here, I give it to processor number 1, then keep walking, stop it, processor number 2, and so on. The PM, on the other hand, requires a different type of parallelization. These are typically done through fast Fourier transforms that are split. They have to split in called slab-like decomposition, which is essentially you give one or more planes to every CPU, right? So depending on how many CPUs you have, in this case you can have 3 slabs, CPU number 1, 3 slabs, CPU number 2, but the number 4 receives only 2, right? So this actually creates imbalances, right? Some CPUs will be computing more than others, and also in this case, even you might have a huge cluster here, and now you need to do more force calculations there. Right? So it's very, very unlikely, and it's actually very hard to split the problem evenly among CPUs. Right? Actually, the way in which you do this might actually be the key factor in which whether your code is good or not. So a full code would look more like this. Probably you have a serial part in which you read the initial conditions or parameter file, initialize something, then you split your calculation, and process number 0 starts working, but it finishes, right? But then the rest is still working, and now processor number 1 is still working, and 2, 3 finish earlier, but they all have to wait for number 1 to finish, because they need then to do a process in which they communicate. Because you're a particle here, you need to know what the force over there is. So you have to wait for the processor that was in charge of that calculation to finish. So the ratio of this calculation to waiting time is called CPU imbalances. Yes? How's a hybrid parallelization? Yes, actually, I'm going to come back to this in a second. So, yeah. Other questions in the meantime? Okay, so this is most likely how your problem is going to look like. So this is actually, there is a law, it's called Amdahl's law, which tells you that for problems like this, the speed up that you can get with an infinite number of cores is never going to be infinite. Right? So actually, you can express it like this. It's very simple algebra. Mind that you have a number of cores given by S, and your code, there is some fraction of it that is not parallel. It's, it's a fraction. So the fraction that is parallel is P, right? So how the speed up that you're going to get using S processors is given by this. And if you notice that you take the limit when S goes to infinity, essentially infinite number of processors, this goes to 1 over minus P. So this never goes to infinite, right? So imagine that you have a code and 5% of it, or 95% of it is really excellent, with an excellent parallelization, and 5% is not. The maximum speed up you're going to get, even with an infinite number of CPUs, is 20. You cannot get it to be faster than 20%, right? So this is essentially because all the serial parts actually starts dominating, and that, and actually this is the case in cosmological embodied codes, and actually it's even worse than that, because there are some parts of the code that not only can be parallelized efficiently, but also that the communication between processors actually increases when you increase the number of cores. Now, so you can imagine that if you want a pairwise communication, the number of bits that you would need to transfer would scarce like the number of CPUs squared. Right? And actually, when you start solving a problem and you increase the number of CPUs, actually it's not unlikely that given to the time of execution would go down, but eventually it actually starts increasing again. So you might be using more CPUs, might be leading you to slower results. So this is actually what shows you what I was describing you for 2 embodied codes. And this is the time that took to run a simulation as a function of the number of cores that you use it. At the beginning, so this dashed line would be a perfect scaling, right? So then as you increase the number of threads, right? So the code works very well, and the time starts going down. But actually, you can see that it starts slowing down, and there is actually a plateau. So when you have, for instance, for this code, if you solve your problem with 64, 128, or even 512, actually the time that it takes does not really improve. Right? So this is actually, imagine that what would happen if we go to 100 or to 10 million CPUs. Right? So it's not only our codes, but in general, scientific codes have hard time properly using these simulations, this hardware. So to be able to use it efficiently, you need to understand a little bit more about computer architecture. And nowadays it's very diverse, but they can be grouped roughly in 3 classes. So you have clusters, or also called distributed memory machines. So this is essentially a bunch of desktops connected to each other, right? Usually you have, you can even connect them through Ethernet cables, but usually they have high performance network interfaces, but they're relatively cheap to build, and they scale very quickly, right? So you can actually add more and more of your desktops if you want. Another solution is to use multi-core machines, which is essentially your laptop is a multi-core machine, where you have more than one CPU. As I was mentioning, you can get up to 100, and they all see the same amount, the same piece of RAM, the same memory. They can access and read the same memory, so they share their memory. Whereas in the previous case, each desktop had its own memory. And then the third class is accelerator machines. It's like in this class you find the GPUs, the graphic processing units, or Xeon Phi, in which you have essentially many of these cores, about even 2,000 or so, that can access very quickly, and they can do many calculations very quickly, but they have very little memory. So these are they are great in certain aspects. They're very fast, but they are relatively hard to code for. So they have a very specific languages, and it's very different the way you code an accelerator than the way that you code a normal computer, a normal CPU. But Actually, in most of supercomputers, it's not like they choose one or the other, but actually they have a hybrid approach in which you have one node, usually it's called, that has typically a multi-core CPU, has a memory, and has an accelerator. So here you might have 24 CPUs, all of them accessing the same amount of memory, and they can give computations to the accelerator. But then there are many of the same, right? And they connect through each other, they know about each other through this fast interface, network interface. So that actually makes it relatively hard for us, right, the scientists, because you have to mix different programming approaches, and this goes back to your question. So typically, if you want to take advantage of these multi-core machines, you have to do things like POSIX threads or OpenMP. They're relatively easy. In the same code, you actually can do even compiler directives to take advantage of this. And then when you want to do distributed memory computing, now you need to do something called message passing interface, or MPI, which is actually sending messages. Here you send 3 bytes here, then 10 bytes here with information that you actually need. So this is relatively hard because this is not to be done by hand. You have to decide what message to send from which CPU to what other CPU, right? So you want to, for instance, be computing, they do the PM part, for instance, and then now you want to take your particles that you hold, and then you deposit them on your grid, and then decide you're going to send the deposited grids to the other CPU. Or you can decide, no, I'm not going to do the deposit myself. I'm just going to send directly the particles to these 2 CPU, and then they do the calculation, then they combine them, and then give them back to me, for instance. So these are actually your choices, and actually that's what makes it hard. And then you have accelerators, and if you want to make use of them, you have to talk about things or languaging programs, programming languages such as OpenCL, CUDA, or OpenACC, right? And most likely you need to do hybrid codes that do hybrid programming approaches. And actually, this is what a group in Zurich did to be able to do what is the largest simulation in the world by now. It's the Euclid flagship simulation that involves about 1 trillion particles in a 4 gigaparsec box. Okay, so in a summary, so the current trends on computer architecture are likely to just continue. So if you want to be able to use HPC in your own research, not only in computational cosmology, learn this parallel programming and the concepts behind it, and also it's very important that to realize that an algorithm and a code that works on your laptop most likely will not work in a supercomputer, and actually what works on a small number of cores most likely will not work on large number of CPUs. So you have to be aware of it, and also you need to know about your hardware, because always the best strategy for parallelization depends on the hardware that is available. So if you're interested in these things, I think these are some points to keep in mind. Okay, so going back to science now. So there was any question about this? Okay, so now we have all of the simulations, and roughly they can be split into 2 groups. One, you have this, well, we call them full box simulations, where you simulate a huge part of the sky or of the universe. And others, they're called zoom in which you go and put all your computational resources to simulate one particular object, right? And you resolve that like a single dark matter halo, which much higher resolution that you could achieve if you had done the full volume, right? So these 2 types of simulations serve roughly different purposes. With these large-scale simulations, we can predict the nonlinear state of the full field, the velocities, the abundance and properties of these dark matter halos, these collapsed structures, and where galaxies will form. And this is actually very important for different physical and cosmological probes, baryonic acoustic oscillations and galaxy clusterings, or the abundance of clusters, something that Rashid was talking about yesterday that Rosita will do. Actually, you have to compare the measurements with predictions from numerical simulations, in particular from this type of numerical simulations, or with gravitational lensing. So the galactic type structure, the zoom-in ones, they care more about the internal structure of dark matter halos, what the density profile is, and the velocity profiles, or how much of structures it have. And this is very important for other type of probes, mostly related with the nature of dark matter. For instance, in direct detection of dark matter, you need to know the amount of dark matter and the velocity distribution that you expect dark matter to have in the local solar neighborhood, or for indirect detection, you would like to know what is the expected density at the center of the Milky Way, because that's going to be telling you how many gamma ray photons you expect if dark matter self-annihilates, or how the nature of dark matter affects the rotation curves of galaxies or the abundance of dwarf galaxies. So from these two types of simulations, this is what we have learned. So first, that the most basic nonlinear units of the universe are called dark matter halos. These dark matter halos form in a hierarchical manner, means that small scales form before than, or small mass halos form earlier than large mass halos. This actually is a genetic prediction for any power spectrum that has more structure on small scales than large scales. So you see here this example of that. So small halos start forming before, and then the growth proceeds hierarchically, means that these small structures will merge, will form larger halos, and these larger halos will merge with another large halos and form even larger structures. So the growth is mostly inside out. It means that the small parts of halos form first, and the outer parts are going to be accreted later on. This happens almost all the time, except on major mergers, where there's only in those situations where you have really mix of material. But major mergers are very, very rare. Doesn't really, actually, they don't happen very often. So in halos, the formation redshift of halos depends on their mass. So even at redshift 0, the high mass halos have a low redshift formation. Low mass halos have a high redshift formation, and that's why they tend to be denser. And they also host older galaxies. But not all the material in the universe is in form of halos. Actually, at high redshift, because around redshift 8, 50% of the material is not in halos. And by low redshift, it's still like 20% of the material is not in halos. Right, so we know that these are the structures, the dark matter halos are these nonlinear structures, and counting them in is actually one of the most basic and actually one of the most important properties of this nonlinear field. This is it's called the mass function. That tells you how many halos there are per as a function of mass. And now we can understand that pretty well. This is the result of 3 different simulations that cover all the way from 10 to the 9 up to 10 to the 16. Again, this is the type of quantity that we need to predict for surveys like eROSITA. And we can, by comparing simulations of different sizes and resolutions, we can quantify also the amount of numerical artifacts. Here we see that these numerical simulations agree only when the halos are resolved with hundreds of more particles. I don't think I have much time, so I'm going to move more quickly. So now these dark matter halos have a smooth component. So this density, we can plot, for instance, the density profile. So the density is a function of distance from the center, and it has this characteristic shape. In the outer parts, it has a slope of -3, r to the -3, and the central parts is roughly r to the -1. So this can be described by this simple functional form. This is the very famous Navarro, Fenk, and White profile, NFW profile, that was noticed by them back in the 97, I believe. So means that halos are very dense in the center, and they decrease as a power law the density in the outskirts. And this functional form seems to be universal in the sense that halos of all mass tend to have the same structure, and regardless of the cosmology and whether you use more dark matter, less dark matter, or even if you change the nature of dark matter from warm or cold, they seem to have always the same structure. This is a very puzzling result of why they have this such a universality, and actually also areas of research where they try to understand the nature of this. You can skip that. But halos are not completely smooth. They have a lot of substructures. So you see all these small clumps. These are the remnants of the merger events. So you had a halos that start forming hierarchically, and a small halo, for instance, fell in, and actually then all the outer part materials start to be stripped out. But the core of that subhalo survives, and that's what forms the substructures. And now this is what hosts, for instance, the satellites of the Milky Way. So the amount of substructure actually follows like a power law, that we have many more substructures of small mass and high mass. But they're not uniformly distributed inside the halo. They have actually this density profile, number density profile, where most massive subhalos tend to be in the outskirts, and the least massive substructures tend to be closer to the center. So typically, the substructures are going to start orbiting, and on average, they lose about 90% of their mass every time they go through a pericentric passage. So they very quickly start going down in mass, and then you start stripping them out of the material until eventually get completely tidally disrupted, and then they form like streams in halos. Let's skip that. Okay. Well, I think I'm gonna stop here. Right. So now these dark matter halos, these dark matter subhalos, have actually internal structures that are very similar to the structure of isolated halos. So they also follow like a Navarro-Frank-White profile, but they are truncated in the outer parts, right? So these are this is the density profiles of substructures of different mass, and then you can see that in the outer parts this would be like NFW, and then they're keep truncated roughly at the places where the tidal field equals the internal gravitational forces of the subhalo. Right. So I was in this lecture. In the final part, I was telling you how we have used these numerical simulations to make predictions about fundamental aspects of the universe. Right. So we need to know. We're making predictions for the signatures of dark matter annihilation, or what to expect for direct dark matter detections, or what the predictions for the E-Rosita clusters will be, or for the Euclid mission. So then it becomes really important not only make one simulation of one type with the simplest flavor and then make predictions based on that, but it becomes also very important to start varying our assumptions, seeing if we change the nature of dark matter, whether the predictions are the same or are different, can we distinguish them, vary start including baryons and so on. So in then, I think probably we'll leave it for the next lecture, but in the next lecture, we're gonna take our assumptions. That was our simulations were called collisionless, with dark matter only, Gaussian initial conditions, GR, and they were classical particles, and I'm gonna describe how we can drop these assumptions and what the end result of that is. So I think I'm gonna stop here. I think it's time, no? And so we continue later today. So thank you. So I don't know if there are questions. Yes. So for the Aquarius halos, right? Actually, this is the Aquarius halos. Yes. Okay, right. So the question is, what advantage has an NFW profile over a Hernquist or isothermal profile? So these lines are actually not the fit. They are actually the measurements of the density profile. So if you go more in detail, here we show actually different curves, which is solving for the same halo with different number of particles in different resolution. Right? So you see that the curves start peeling off. That actually is you start seeing the effects of the finite force resolution. But the places where the results are converged, they follow essentially the same line. So then you can try to see and fit or see whether this is well described by Einasto or Hernquist or isothermal. And then you see that at this resolution, essentially the Hernquist and the isothermal are actually very poor descriptions of the actual density profile. And the NFW that was proposed 10 years before this, it's actually a very accurate description that this is actually very close to -1, this the actual measured slope, and -3. But actually, if you go start seeing on detail, you start seeing that it's actually not quite correct. So the slope is never really -1. It's actually smoothly varying and goes asymptotically. Well, actually doesn't really have a clear asymptotic limit, and it's actually better described by a smoothly varying slope. So in this case, this NFW has these two clear asymptotic limits when R is much smaller than the typical scale of the halo. Goes to -1, this term is 0, and when R is larger than Rs, this term, then you get, essentially this is approximated as R plus Rs, this one goes away, and you get 1 over R cubed. Right, but when you start seeing this, you see that the slopes, the symptotic slopes are not quite correct, and this is a better description. So it's something that the slope is slowly varying as a function of radius, and this is called the Einasto profile. That was proposed by Jan Einasto for a different problem, but turned out that it describes more accurately the density profiles than simple NFW. But these are kind of second-order differences that you see only when you do very high-resolution halos. When you do lower resolutions, then you can distinguish that the Hernquist and isothermal are not really good descriptions, but it's very hard to distinguish between Einasto and NFW. More questions? Yes? Right. So he's saying that right. So when we were discussing parallelization, we were essentially taking different chunks of this, or we were splitting this domain, and then we were assigning it to one CPU. So he was saying, what about if we split it into smaller chunks and we put them on essentially in a sorted list, and we have now a number of processors that they start grabbing these chunks of these units to be computed, and then when you're done, you kind of go up and get the next one. And the question is whether that would reduce the amount of CPU imbalances. So the easy answer is yes. Actually, that is something used by a more modern embodied code. It's called a kind of graph-based parallel computing, in which you actually try to build something actually not so different to this. So you actually build the whole algorithm, and you build essentially as like a graph with different interconnections. So you know exactly what data dependencies there is between different chunks of computational units. And then you have a pool of computing cores, and they will start and they make requests and saying, okay, I'm done. Let's see the next unit that can be completed because all these prior dependencies were met. And then you can start doing this in a kind of task-based parallelization. And that seems to be quite promising, actually. And these people claim that they can get better scaling. And actually, this code here, Swift, the one that's blue, actually implements all these ideas of graph-based parallelization. And it's actually public. You can go to their website. But you see that even then, even though you are doing this, it's very hard to get something close to a perfect scaling. And one of the reasons for that is that I think in all these embodied codes, the type of algorithms are very different. It's not that you have one type of algorithm and you want to make it optimal. Actually, you have many different types of algorithms. You have, well, you already discussed two of the PM and the tree, but also the way that you decompose the domain is actually not so trivial and actually spend some time, so that involves different calculations. And then you have all the analysis tools. You need to identify the structures and the halos that I mentioned earlier. So you need to find that to actually search them, and that's another different type of algorithms. And then you want to measure correlation functions or power spectrum, and it's a different type of algorithms. So it's very, very heterogeneous codes. And for them to really scale well, every single part of the code needs to be to scale well, which makes it a hard task to do it. But yes, I think this is going to be a problem to tackle in the future. And also another problem that perhaps even more important is that all these future codes will need to have some sort of redundancy. Because now imagine running your code in 100,000 CPUs. It's very likely that, and you're going to run them for a week, for instance. So it's very likely that over the time of a week, with 100,000 CPUs, one of them will crash, right? One of them will fail. A cable will be faulty, right? So what are you going to do? Are you going to lose all your calculation and you're going to stop there? Right, that probably is going to be very inefficient. So you probably would need to have some sort of redundancy, that the same piece of code of memory is actually in more than one CPU. So in case of one of them fails, you can actually recreate that part of missing information, and then your calculation can continue. So this is another challenge for the future, for the next generation of computing, of numerical simulation codes. This is a plot actually done by the Swift code people, and yeah. So I think that there are two things, right? So one is how the code scales with the number of threads, and that has to do with the way that the code is parallelized. And you see that it's better than Gadget, but it's not that much better. But the biggest difference is the overall offset, right? Even with one thread. And this is mostly due to other type of optimizations that the Swift team has done. Actually, this was a group of astrophysicists together with computer scientists. Actually, a few people from Google were involved, where they were essentially dissecting every line of the code and making it as efficient as possible with vector instructions and many optimizations that for certain type of Intel compilers and CPUs. So I think that that's why they managed to get a code that was much, much faster at the price of or at least it's not obvious how these improvements are going to be when you use it on a more general class of computer architectures, CPU models, compilers, and so on. So the code was just released. I mean, they've been in development for many years. Right, so it's, sorry? Hmm? Right, yeah. So if it's an Intel compiler, it's not free, so you have to pay for it. It's actually not so cheap. And then, and for normal applications, you get typically speeds up of maybe 20% or so. In this case, they are getting this huge factor, but well, personally, I think this would be very problem dependent. And then you have also these different type of choices that you can do, right? So you can write a very general code like Gadget that can do these zoom simulations and full boxes and hydrodynamics and isolate the initial conditions and so on, or periodic boundary conditions, and that's very flexible, right? But of course, if you are very flexible and you tackle different problems, you cannot be very optimized for or you cannot be the most optimal code for a particular subset of problems, right? So you can then have other codes that specialize on a certain problem, and then they can make it more efficient. So you can choose optimization with specialization, or being more general and tackle different problems. Okay, more questions? No? Rishi? So we break for coffee now, or? Yep. Okay.